I'm Jack Wright, and I'm a research fellow at the European Space Agency. I'm talking to you today from Madrid, and I'm very grateful to Mario for that introduction to machine learning. I think you've been learning about machine learning earlier in the school, and I'm going to show you an application of it today, but also this is a cautionary tale. That's why I've given you this humorous title. Does machine learning mean the end of geological mapping? Well, no, actually. Um, and I'll get on to the well, no, actually part towards the end. But before I begin, I'd like to thank my long list of collaborators. Um, Machine learning is something that I'm only just getting into, maybe like many of the people in the audience. So I'm by no means an expert. And it was actually, the work of several people to produce what I'm about to show you. So I'm very grateful to all of them, particularly Alex Barrett, whose paper I'll be mentioning a lot in this work. So I'm going to be talking to you today about a machine learning algorithm that was commissioned by the European Space Agency to produce a terrain classification of the ExoMars Rosalind Franklin rover's landing site. The landing site that was selected is Oxyoplanum. So on the left of this slide here, you can see this figure. Oxyoplanum is the area in this white box on Mars. It's in this wider area colored mostly in green here called Arabia Terra. Arabia Terra is some of the most ancient terrain on Mars, and the objective of the ExoMars mission is to go to Mars and to investigate its ancient terrains to look for signs of preserved life from Mars's ancient past. And Arabia Terra is a particularly good place to look because it's set at a lower elevation than the Mars Southern Highlands. So this is a topographic map of Mars. So cold colors are low elevation and hot colors are high elevation. And Arabia Terra is set at this sort of middle elevation, which means there's a greater depth of atmosphere for the rover to descend through, which means its parachutes are able to work. So this is a place that meets the engineering constraints, but also has that ancient terrain that conceivably could have preserved life from ancient Mars. And on the right, you can see a more detail. The yellow shapes are the landing ellipses for the ExoMars rover, and you can see that they are set at the end of this drainage system that has been mapped called Cugun Vallis, where liquid water flowed. And so liquid water is a prerequisite for life as we know it. And not only that, but it produces minerals such as clay minerals, which have a high capability for preserving biosignatures. So at the end of this drainage system is a really good place for the rover to land to search for clues of ancient life on Mars. So that's the landing site. But why do we need to classify its terrain? Well, I think earlier in the school you've been learning about rover traverses and rover trafficability, and that's one really important thing. We need to characterize the landing site to know that we can land in a safe way. So, for example, we need to know what the topography is, and we need to know that the terrain is stable and safe. And if the rover landed on something like a cliff edge, that would be a bit of a disaster. So that's why it's important to have the landing site's terrain well classified. And more than that, once you've landed safely, you want to be able to find a way through the terrain. And so you can imagine that if the rover were to land surrounded by large wind-blown ripples, it would be far easier for the rover to move between them than to move across them. And so you can use a terrain classification to see these safe routes through the red planet. And another useful outcome is maybe these terrain classifications are useful for helping scientists figure out where the regions of interest are in the landing site so that they can make the first initial plans for how the rover will traverse. And even before the rover arrives, these products might be useful scientifically. And I'll speak more about that later. So these are the good reasons to do these terrain classifications. But the question you should always be asking yourself if you're considering using machine learning is, well, what are the added benefits of using machine learning? Why wouldn't you get a human being to do this? Why would you want to rely on a machine, particularly a machine that maybe you don't fully understand? So the problem we're faced with here is the scale, the amount of data we have and the resolution of the data we have. So I think by now you should be familiar with high-rise image data sets for Mars. These can be 25 centimeter per pixel images, and the example I'm showing you here on the left is about 7 kilometers by 14 kilometers. And each of the pixels in this image are 25 centimeters across. So this is an international school, and I wanted to give everyone as best a sense I could of what 7 kilometers by 14 kilometers looks like. And I was struggling to pick a place that I thought everyone would be able to identify with, but in the end, I just settled for Manhattan Island. So Manhattan Island is about the same size as a high-rise image, more or less. So can you imagine trying to look at each 25 centimeter pixel in Manhattan Island? So looking at this view on the right and classifying each pixel according to the terrain carefully in each pixel in Manhattan Island. That sounds like an awful job for a human being to do. And then the next thing you need to consider is that I'm going to be talking to you today about two places on Mars, Oxyoplanum, which I've already introduced, and Jezero Crater. Jezero Crater, which I worked on, is covered by 4 high-rise images, but Oxyoplanum has about 50. So can you imagine classifying the terrain in each 25 centimeter pixel in 50 7 by 14 kilometer images? This is definitely a problem for a machine to solve rather than a human being. So that's why we're going to address this problem of terrain classification using machine learning. And the machine learning algorithm I'm talking about is called NOAA-H. It's a machine learning algorithm that was commissioned by ESA specifically to characterize the terrain at the landing sites for ExoMars. And NOAA-H stands for novelty or anomaly hunter, and the H at the end stands for high rise. So this is a machine learning algorithm that is trained to ingest as its input high rise images to produce a terrain classified raster. So NOAA-H is a deep learning convolutional neural network. And whenever I started this work, I was no expert in machine learning. So I needed to have all of these different terms broken down. So I'll break them down for you as well. The important thing to take away from the neural network part is that this is a model that learns from a training data set to make its classifications when it's introduced to new data. And so that's what this part of the slide is showing you here. This is the training data set. So human geomorphologists looked at the landing sites in Arabia Terra and decided that there were these 14 important terrain classes that needed to be distinguished by the machine learning algorithm. And in order to train the algorithm, they used these framelets. So these are small subsections of high-rise images, 128 meters across or 512 pixels across. And the human geomorphic expert would map these manually. It's in a process called labeling, and would label the pixels in each framelit according to what class is present. So this is an example of a labeled framelit. And the training data set eventually contained over 1,500 of these labeled framelits. So this is the time-consuming work that you need to front load whenever you're training one of these machine learning algorithms. Once the training has been done, I'll hopefully show you that you can get quite a lot of payoff. So that was the neural network explanation. It's a deep learning machine learning algorithm. In our case, the deep learning part, the important takeaway message is that the model contains many layers. It works in an iterative way to classify the high-rise images. And it's convolutional, which means that it uses filters to do this hierarchical classification. So it might begin by doing some simple edge detection to see some basic outlines, and then it can group those together into more complex shapes, and then it can ultimately come to understand and recognize rather textures. So that's how NOAA-H works broadly. And I'll just run you through the classes very quickly to show you the kinds of things that are in the landing site area that the machine learning algorithm needs to understand. So there are 5 broad groups of terrain that the algorithm can identify: bedrock, non-bedrock, large ripples, large wind-blown aeolian ripples, smaller ones, and boulder fields. So here I'm showing you the bedrock classes, and it can see smooth bedrock where bedding planes are outcropping on the surface, and they are generally quite bright and have this smooth featureless texture on the top. And then in between these fields of aeolian ripples, there is material that looks like bedrock but has a more textured appearance. And then here you can see in rugged bedrock this sort of really rugged material that's outcropping quite strongly from the surrounding ripples. And then fractured bedrock has a really identifiable pattern of polygonal fractures on its surface, and it's quite easy for the AI to identify. The non-bedrock classes are just sort of loose material on the surface of the planet, which can be featureless and flat-lying, or can be lineated where it's forming in the walls of impact craters, and you can see material mass wasting down into the center of the crater, or it can have a more disorganized texture seen in a patch here between two large fields of ripples. The ripples are really easy for human beings and the AI to identify. Here's a field of large continuous ripples. So by continuous, we mean that they join pretty much and cover the whole area that you can see. And by large, these are features that are more than 5 meters across. And then you can see the same features, but isolated from each other in the middle of this frame. So the machine learning algorithm is able to classify the large ripples, but then also able to classify separately the intervening space, which has any of the other sort of large scale classes. So there could be, for example, in this case, fractured bedrock underneath these large ripples. And then on the right, a more minor class is where the ripples intersect at right angles to form cells. And these are called rectilinear, and these are a relatively minor component of the mapping area, the landing site, rather. And then small ripples are just the same, but smaller, as the name suggests. So there's some here in the floor of an impact crater in a continuous field. And then here are some isolated ones again, either with a bedrock substrate, again, in this case, maybe fractured bedrock, and then in this case, some sort of non-bedrock substrate. And then the final group is boulder fields, which only has a single class called boulder fields in it. And so the machine learning algorithm is able to identify boulders in isolation. So, and then whenever you do all of that training and the classes have been decided upon, this is the sort of final product you can get. So this is a terrain classification map of Oxyaplanum with 50 high-rise images. I think it's 49, but more or less 50 images composed. So this is a product that no human being conceivably would be able to make in any reasonable amount of time. And the question becomes, this was a product that was commissioned by ESA for Oxyaplanum for the ExoMars rover mission. And if it's going to be used for rover traversability and trafficability, we want to test that it's actually good. We want to know that it's fit for purpose. Are we going to be able to do that before the rover actually lands? Well, one idea that we came up with was we can transfer it to another landing site where the rover is already there. Unfortunately, the NASA Mars 2020 Perseverance rover has landed in Jezero Crater already, which I think you're all familiar with. I think it's been introduced earlier in the school. So Perseverance rover is on Mars already, and actually, really interestingly, it has the Ingenuity helicopter with it. So this is its landing site, and it landed around here, and it's currently investigating the delta, and we're going to look at what the machine learning algorithm was able to do when we transferred it to Jezero and compare it with images from the helicopter. So on the left, you see a zoom in of our new terrain classification of Jezero Crater. And the red dot shows you where the Ingenuity helicopter is at this particular time. The red bracket shows you roughly what its field of view is in this image. The yellow line are the tracks left by the Perseverance rover, and the right-hand image is an image from the helicopter. So you can see there are these 3 tracks left by the rover. You can see them here, these 1, 2, 3 here. And so the helicopter is looking in this direction. And from orbit, from high rise, the terrain classification algorithm has identified basically everything in the field of view as being fractured bedrock. And when you look in the helicopter image, you can see that there's a thin covering of non-bedrock material, but underneath you can see that the bedrock geology is exposed here, and you can see its fracture pattern. And what I find interesting is that in high rise, this fractured bedrock looks like it could be quite scary terrain for a rover to cross. It looks really jagged. It looks like it wouldn't be traversable, but the rover tracks here demonstrate beyond all reasonable doubt that this is easy terrain for the rover to cross. And not only that, but the machine learning algorithm has correctly classified this region. So that's a nice result. We can go for an even longer flight. So on the left here, again, I'm showing you the terrain classification. The red line is the path that the helicopter takes. We're going to start at point E, and again, the yellow line shows you where the rover has gone. So it does this little loop here on Sol 129. You can see that little loop here on the screen, I hope, as well. So the helicopter takes off in an area that the machine learning algorithm classified in green. This is one of the non-bedrock classifications. So you can see that this is loose material. There's no bedrock exposed here. So that's a good classification. And in the distance, you can see here bedrock outcropping. So we'll move to point D. So you can see here that we're on top of the bedrock. And now we're looking off into a region with sand on the surface. And on the right, you can see these large ripples have formed with sort of parasitic small ripples on top. And on the left, there's a smaller, a field of smaller ripples. And if we look at the AI terrain classification, you can see that it's really captured the large ripples on the right-hand side really nicely. That's really good work. On the left, it's classified some of this region as small ripples. That's this blue color, but a lot of it is this green color. And again, those are the non-bedrock classes. So what seems to be happening here is whatever characteristic feature it is about small ripples that the terrain classification algorithm NOAA-H relies on to diagnose small ripples isn't present here enough that it can see them. Maybe it's too small. And so it's misclassified this area as non-bedrock material, but ripples are non-bedrock materials. So this is not a very bad misclassification. It's just that maybe if it was trained on these smaller examples, it would have been able to identify them no problem. So maybe with a little additional retraining, this transfer would have worked even better. But this is still a very good result. And we can fly even further towards the end of the flight. So again, the helicopter is here at point B. It's looking ahead, and you can see this sort of boomerang-shaped outcrop here. Here it is here, and it's this rugged bedrock class that's jutting out of the landscape. And this is more difficult terrain for the rover to traverse. And what we've seen looking at the Perseverance rover's traverse so far is that the team is guiding it through material that NOAA-H has classified as fractured bedrock, like I showed you earlier, but they seem to avoid, where possible, this yellow unit, this rugged bedrock. So again, this is an important result for ExoMars. So we were able to test the capabilities of the machine learning algorithm by just looking at images from the ground taken by Perseverance, and that's quite good. And we wanted to come up with other ways to test its capabilities. So on the left here, you can see the complete Jezero product. So there are 4 high-rise images here that have been classified by NOAA-H. And I'm showing you here not the 14 classes, but the 5 groupings. So non-bedrock, bedrock, large ripples, small ripples, and boulder fields. And on the right, I'm showing you a completely different product. This is a human-made geological map. This is made by Stack et al. 2020. This is a paper and a map written and made by the Mars 2020 rover team based on high-rise images. And they were a team of 63 mappers. They divided this area into 166 little quads. They subdivided it into these quads so that each mapper could map a few of them to stitch all of the maps together to make the final product. This would be too big an area for a single human to map. And so 63 mappers, 166 quads, each 1.2 by 1.2 kilometers in size. And it took them the better part of a year from, I think it was May 2019 to April 2020 to produce this product. And I've colored it so that the colors on their map correspond roughly with the colors on my map. This isn't their full geological map. This is a geological map of the surface materials, or what we would call on Earth the drift, the unconsolidated material on top of the bedrock geology. So in green, we have their sort of smooth, loose material. In blue, we have their large aeolian bed forms, which corresponds roughly to our large ripples. We have their small aeolian bed forms in a sort of cyan color, which corresponds to our small ripples. They mapped talus, which are, the loose material on steep slopes, which we have loosely correlated with boulder fields, because many of these talus slopes do indeed contain boulder fields. And you can see boulder fields are picked out in black around the distal part of Jezero Crater's delta, and you can see the talus slopes are here as well. And where they do not map a surficial unit, we assume that that means there's exposed bedrock, and so we color their no surficial unit as red, which is equivalent to our bedrock. And I hope you agree that at this sort of zoomed out scale, the machine learning algorithm has been able to produce a product that's remarkably similar at this scale to the human-made geological map. And the human geological map took a year to make. The machine learning algorithm had already been trained in Oxyaplanum. And so when we transferred it to Jezero with no additional training, it only took the length of time it took to classify the individual images, and there are 4 of them here, to make this product. And it took about 15 minutes to an hour to make an individual image. So it maybe takes a morning or an afternoon to make the 4 images, and to stitch them together is the work of maybe, an hour or an afternoon at most. So in a day, say, we were able to produce what took the human beings, a year to produce, or so it would seem. And I will come on to the no actually part very shortly. Now, we were just eyeballing that, but we were just looking at it to compare them qualitatively. But can we do any better than that? We can quantitatively compare the 2 products by creating something called a confusion matrix. Now, the takeaway message from this matrix here is that we have an expertly created product, the human geological map, and we divided it into pixels that overlap the pixels in the classification of the NOAA-H products. And for each pixel that the human beings classified as being, let's take the example of the large ripples, say. For each pixel that the human said was large ripples, how many pixels did NOAA-H agree were large ripples? And the answer here, to give you an idea of how many pixels we're talking about, is over 650 million. Okay, so we're talking a lot of pixels. And that actually means that's a 79% agreement. That's a really good result for machine learning. And then the other numbers in this row are misclassifications. So about 1 million pixels that are actually large ripples were misclassified as boulders. Well, that's a really insignificant fraction of the correct response. So the machine learning algorithm for the large ripples is working really well. And you can see these percentages of precision here. Precision is a statistic used to measure the quality of a machine learning output. And precision, in our case, basically means if NOAA-H has found a class in a given pixel, is it the right one? And so 79% of the time for the large ripples class, NOAA-H is getting it right, which is good. And then another statistic we can use is called recall, which in our case basically means how much of a given class does NOAA-H find? Is it able to find all of the class that is present? And again, very good statistics for large ripples. There are classes that perform less well, obviously. So for example, I said about the talus slopes. So Stack et al. Classified talus slopes. We were classifying boulders. There's not a one-to-one correspondence there, which explains the poorer precision and recall for these classes. But that's not important. That's a misclassification that we can understand. So the important thing is that the biggest numbers in each of these rows and columns should be lying on this diagonal. And except in the case of the small ripples and the talus, which are very minor components of the mapping area, this is true. The big numbers are on the the diagonal. So that's a really good quantitative measure of how well the algorithm is performing. Okay, so to end the talk, we're getting to the well-no actually part. Has the machine defeated the human beings? It was able to produce a product that looks really similar to a human-made geological map that took a long time to make. Well, no. During the course of this winter school, you've been learning how to make a geological map. And at the same time, you've been learning how to understand rocks as three-dimensional volumes that go into the subsurface. You're understanding where the rocks come from and how they form and how they've evolved into their present state. And you understand that geological events take place in time and they have a sequence. So you understand that the rocks not only lie alongside each other, but lie on top of each other. And the rocks at the top of the stratigraphy formed more recently than the rocks at the bottom of the stratigraphy. The AI has no concept of any of that. So it doesn't know how these rocks formed or how these surface textured formed. So for example, here in this image on the right, it's showing areas that basically all covered in ripples. You will know that these are formed by wind and that they are non-bedrock material, but it's misclassified some of them in Jezero Crater as these in this yellow class, which is rugged bedrock. And that's because there've maybe been intersecting ripple crests, which give a sort of rugged appearance in a purely descriptive sense, but not in any way that human beings would recognize as ripples overlapping turn into solid rock. So it has no concept of the origins of the textures, so it occasionally makes these sorts of errors. And like I was saying, it doesn't understand that they're three-dimensional rock volumes. It doesn't understand that they take place in a sequence in time. And so based on the human-made geological map, the humans were deciding between two scenarios about what order the rocks formed in. The AI has no ability to do this sort of work. And it certainly can't produce these cross-sections or these correlations of map units across vast areas of space. So that's the real value I hope you've taken away from this school of making a geological map, coming to understand the geological history of an area, which is something that machine learning is not capable of doing yet. And then another thing is, I said this product on the right is 25 centimeters, sorry, on the left is 25 centimeters per pixel. And the product on the right has less detail. Well, what you need to ask yourself is the detail on the left correct? I showed you in the confusion matrix that many pixels are misclassified, even though the overall picture is correct. And then human beings, this is too much information for a human being to ingest, which is why geological maps are summaries and they're human ingestible and they can be read easily by a human being. This is not really a legible product. So that's another thing to consider. So I'm coming to the end of my talk. I just wanted to show again, we successfully made a machine learning terrain classification of Oxyoplanum, and we tested it by looking at Jezero Crater on Mars. So we can say with confidence that this is going to be a useful product for planning rover traverses when Rosalind Franklin arrives on Mars. In the meantime, it might actually be a useful product to aid geological mapping of the landing site and get it started. The mapping team has had to rely on non-experts to produce this, to generate enough people to get it done in time. And maybe this would be a useful kind of product to aid and speed up that process. But it's no replacement for geological mapping per se, because we need to understand rocks as three-dimensional volumes that form in time. And I did say that, it might also have its independent scientific use. And just to give one example, Eleanor Favreau, who is a co-author on the Barrett et al. And the Wright et al. Papers about Oxyoplanum and the Jezero products respectively, she is using the machine learning algorithm to look at the periodic bedrock ridges in Oxyoplanum to tell us about the clay-bearing rocks in that area. So already being useful as a scientific product. So with that, I will finish. I have some references, but I'll just end there. Thank you.